Hello. The title of this investigation is Study of the Friction Behavior of Tungsten Carbide and Cobalt Drilling Tools during Machining LC Cast Alloys. LC cast alloys are widely used in the automotive and aeronautical industries due to its good lightness-strength balance. However, there are problems with the machining of these alloys. Added to this, in the drilling process there are problems with chip evacuation. A solution to these problems is to reduce friction at the chip tool interface. One of the directions to achieve this is to improve the surface conditions of the tool flute. Therefore, it is necessary to analyze the friction in the tool chip interface. This is governed mainly by two theories: the adhesion theory and the asperity interlocking theory. The objective of this work is to develop a mathematical model by which the friction in the chip tool interface can be simulated by relating adhesion theory and asperity interlocking theory. To simplify the model, the drilling can be considered only as an orthogonal cutting. There are different models to obtain the friction at the chip tool interface during orthogonal cutting. The models to use are the Childs friction model based on the Coulomb model, and the Ernest and Merchant model, which is obtained from a force analysis. The adhesion theory does not include roughness. However, some authors show that the behavior obtained by plastic contact is similar to the adhesion behavior. Taking this into account, the Kragelsky plastic contact model will be used, which includes a series of surface characteristics, in addition to the equations that can be expressed as a function of the area relationship. The procedure is the next. First, the foundation of the model is established. The second step is the development of the model. The third step is the characterization of different roughness profiles obtained from the flute of a tungsten carbide and cobalt tool. And finally, the construction of graphs of the theoretical stress friction and the theoretical chip sliding velocity versus flute surface roughness. It is considered that the contact between the tool and the chip is governed by the characteristics of the roughness of the tool and the mechanical properties of the chip. As a result, the models are presented. The Childs model is taken as a basis. In the asperity interlocking model, a substitution of the corresponding coefficient of friction is made, while in the plastic contact model, the Childs model was modified to consider the relationship of areas, and thus integrate the equations of the Kragelsky model. Various roughness profiles were obtained from the tungsten carbide and cobalt tool flute, which initially had a roughness of 0.3 micrometers Ra. A fine polishing using pecan shell reduces the roughness to 0.03 micrometers Ra. The profiles were analyzed and the surface characteristics necessary to use the plastic contact model were obtained, and the average angle of the asperities for the interlocking model was obtained. The three graphs of the friction behavior for the different work materials are presented. The difference between the graphs is found in the different values of the shear strength of each alloy. At low roughness there is adhesion due to the increase in the contact area. As the roughness increases, the friction decreases and allows the chip to slide. The minimum friction is found at a roughness of approximately 0.2 micrometers Ra. If the roughness continues to increase, the friction increases, and a ploughing action occurs. The crossover between the two models is similar in all three cases, due to the similarity of their properties. as the Poisson's ratio and elastic modulus. This behavior has been presented experimentally in works such as that of Rabinovich in 1991. However, it had not been theoretically contemplated involving both theories and much less applied to machining. The theoretical chip sliding velocity was obtained through the Ernest and Merchant model with the friction and shear angles. It is considered that the rake angle will be approximately equal to the helix angle of the tool, which is 30 degrees. For the three alloys the behavior is similar, so a single graph is taken as a reference. As the roughness increases, the chip sliding velocity increases. The maximum chip sliding velocity is approximately 0.2 micrometers ra. If the roughness continues to increase, the chip sliding velocity of the chip decreases. Therefore, the optimal flute surface roughness when machining LC cast alloys with tungsten carbide and cobalt tool is approximately 0.2 micrometers ra.